Hello students! I would like to discuss one of the questions that deal with spectral utilization. This exercise requires some simple calculus skills and might be considered rather difficult for some students. Note that we only have 3 exercises out of over 180 exercises that require calculus skills. So please don't be scared by it. Here I will explain this exercise in great detail. Here you see an AM 1.5 solar spectrum. How much power per area and photons per area are in a standard AM 1.5 solar spectrum? That are the questions we are going to tackle here. I have included this exercise in the course as it provides the students an easy tool to determine the numbers of photons in the spectrums which we need to calculate the theoretical potential short circuit density of a PV device. In week 3 we will come back to this, as then we introduce the external quantum efficiency of a solar cell, which we need to calculate its short circuit current density. The unit on the vertical axis is the spectral power density and has the unit watt per square meters per meters. The per square meters reflects per area and the per meter reflects the spectral range. This unit gives the power density per spectral range. Why is this important? The sun or any light source does not have the same constant power in the different ranges in the spectrum. As you can see, the solar AM 1.5 spectrum has the highest power densities in the visible part from 400 up to 700 nanometers. To make a simple estimation of the irradiance, we simplify the spectrum with 2 rectangles, one going from 250 nanometers up to 1000 nanometers and one going from 1000 nanometers up to 2000 nanometers. Using this simple approximation, we are able to calculate the irradiance and photon flux and have a first estimation of irradiance and photon flux of a typical AM 1.5 solar spectrum. The irradiance is the integral in the wavelength space over the power density function, or in simple words, it is equal to the area under the power density function. As you can see, we have 2 rectangles, so the area under the 2 rectangles is equal to the irradiance. Let's make a calculation. The area under the first rectangle is the product of the height and the width and gives us 750 watts per square meters. The second rectangle has an area of 250 watt per square meters. This gives a total area or irradiance of 1000 watts per square meters. This is exactly the same irradiance as for the AM 1.5 over the entire spectral range. The next question is, what is the photon flux? To determine the photon flux, we first need to determine the spectral photon flux. For that we need again the spectral power density function. The energy of a photon at wavelength lambda is the product of the Planck constant h and the light velocity c divided by the wavelength lambda. So the spectral photon flux at wavelength lambda is the power density at lambda divided by the energy of a single photon at lambda. Or in other words, the spectral power density p lambda times lambda divided by the product of the Planck constant h and light velocity c. This gives the spectral photon flux. These are 2 increasing lines which, when extrapolated, would intersect with the origin of the graph. Again, the photon flux is the integration over the spectral photon flux, or in other words, the area under the graphs. The area under the spectral power density can be divided in one rectangle and two triangles. It is a relatively easy job to calculate the area. The total area here is equal to the photon flux of 4.2 to 4.3 times 10 to the power 21 photons per square meters per second. Note that this is within 2% of the real value of an AM 1.5 spectrum up to 2000 nanometers. This shows that a spectral power density of two rectangles as presented here in this exercise is a reasonable approximation of the solar spectrum. You can solve this exercise using calculus. I will give a very short introduction on some very simple principles of calculus here. Please don't tell your math professors, because they won't like my simplifications. Consider the three polynomial equations shown here. The first function is constant with x. Fx is equal to c. The second function is linear with x. Fx is c times x. Third function is quadratic. Fx is c times x squared. The question now is, how can we calculate the area under such function between the boundary conditions x is a and x is b? Let's consider the general polynomial function c times x to the power n. N can have all values except minus 1. The integral of such function is given by c divided by n plus 1 times x to the power n plus 1. The area between the boundary values x is a and x is b can be calculated by subtraction of the integral function at x is b minus the integral function at x is a. For a polynomial, this looks like this. It looks maybe complicated, but it is rather simple. Let's give some examples. First, we consider the function fx is constant, c. In this case, n is equal to 0. Using n is equal to 0, we can deduce the integral function. The integral of this function is c times x. And if you would consider the area between the boundaries b and a, this would be c times b minus a. Now we consider a linear function. Fx is equal to c times x. For this function, n is equal to 1 and the integral function equals half times c times x squared. The area between the boundaries a and b is in this case equal to half c times b squared minus a squared. Finally, we consider a quadratic function. Fx is equal to c times x squared. In this case, n is equal to 2. The integral function of this function is c divided by 3 times x to the power 3. The area between the boundary conditions a and b is c divided by 3 times b to the power 3 minus a to the power 3. Let's go back to the irradiance. Using calculus, we can arrive at the same answers. First, the irradiance is the integral over the power density function between the boundaries of 250 nanometers and 2000 nanometers. We can split this function in two different regions or two different integrals. One between 250 and 1000 nanometers and one between 1000 and 2000 nanometers. These functions are constant, so the integral is linear with lambda. Working out these integrals gives 1000 watts per square meters. The spectral photon flux can be described by two linear functions going through origin. First, the photon flux is the integral over the spectral photon flux between the boundaries 250 nanometers and 2000 nanometers. We can split this function again in two different regions or two different integrals. One between 250 nanometers and 1000 nanometers, and one between 1000 nanometers and 2000 nanometers. Since the spectral photon flux is linear with lambda, means that the integral is half times lambda squared. Working out these integrals gives 4.25 times 10 to the power 21 photons per square meters per second. The same answer as we deduced earlier. Now we have solved the exercises using calculus. If you think this is too difficult, don't worry. Only 3 out of over 180 exercises uses these calculus skills, and it does not get more difficult than what I have shown here in these examples above.